Hi guys, and welcome back to my channel. This is the detailed revision guide of the Glaciated Landscapes and Change series over here on my channel. We've already done a load of the in-depth videos over here. I'll try and remember to link the playlist up here of the glaciation videos for you, so go ahead and watch them. This is just going to be about an hour-long roundup of everything you need to know for your exam. I'm also going to do the essentials, so even smaller, in probably 15-20 minutes after this video. So I hope you enjoy. Subscribe down below if you don't want to miss that. And without further ado, let's just get straight on into this video. The world is currently in an interglacial period, meaning temperatures are higher and the majority of our glaciers are retreating. Historical periods of glacial advance and retreat. Glaciers have advanced and retreated in correlation with the world's glacial and interglacial periods. Currently, the majority of glaciers are thought to be retreating due to increased temperatures. Historically, global temperatures have been increasing since the last glacial maximum. However, there have been smaller global coolings in recent history that have affected the mass balance of glaciers. The Little Ice Age between 1300 and 1870 has been the most significant global cooling period in recent history. This graph shows the length change in 5 different glaciers in Mont Blanc in history. From the period of 1818 to 1821, during the Little Ice Age, it shows that all glaciers were at the largest point at this time. Glacial advance in the Alps was a very prevalent issue during the Little Ice Age. Heavy snowfall and avalanches were common and pose a risk to life. Between 1627 and 1633, Chamonix lost a third of its land through avalanches, snow, glaciers and flooding, and the remaining hectares were under constant threat. Long-term causes of glacial periods. One piece of evidence to explain long-term climate change is the Earth's Milankovitch cycles. Milankovitch theory of astronomical climate forcing states that when the global energy alters, the consequent variations in the Earth's orbit force global changes. These changes involve stretch or eccentricity. This is when the Earth's orbit changes from circular to an ellipse every 96,000 years, which changes the distance between the Earth and the Sun. Therefore, the Earth will be closer to or further away from the Sun at different points during the different orbital shapes, affecting the climate. For example, if the Earth is closer to the Sun, the Earth will receive more solar radiation and therefore be warmer. The second theory is tilt. The Earth's tilt changes between 21.8 degrees and 24.4 degrees every 41,000 years. If the tilt is greater, the tropics receive more energy and thus become larger. Third, wobble or axial precession. Over time, the direction in which the axis tilt changes in the same way that a spinning top moves. In 22,000 years, the axial tilt spins one whole time around. This does not affect how much sun the Earth receives overall, only where solar radiation is distributed, in which hemisphere. Short-term causes of glacial periods. The short-term causes of glacial periods include variations in solar output. Energy output from the sun is not constant. Sunspots occur by magnetic storms, forming dark areas on the sun, which increase solar output. The number of sunspots increase and decrease in an 11-year cycle. Sunspots aren't regular and can vary. During the medieval warming period, there were high numbers of sunspots, but during the Maunder minimum, there were very few sunspots. Secondly, volcanic eruptions. For instance, Mount Tambora in Indonesia erupted in 1815 and lowered global temperatures by 0.5 degrees Celsius. Initially, scientists thought the acid produced would block some solar radiation, hence cooling the Earth. However, it is actually sulfur dioxide, a potent greenhouse gas, which is released during an eruption that reflects radiation for several years. The Holocene epoch. We are currently in a Holocene epoch, which is an area of limited ice cover lasting over 10,000 years. The last glacial and ice covers exist in polar, alpine and periglacial environments. Polar environments. Current distribution. Polar environments are located at the poles, the high latitudes of the Earth within the Arctic Circle, above 66 degrees north, and the Antarctic Circle below 66 degrees south. These environments can also be described as being within the 10 degrees isotherm, which means in the hottest month, the average temperatures stay below 10 degrees centigrade. However, the first definition is the most common. In polar regions, the maximum extent of ice sheets extends within the coldest winter months. The Arctic winter in the northern hemisphere occurs from December to March, and the Antarctic winter in the southern hemisphere from March to October. Characteristics: climate. Due to the constant below freezing temperatures with little rainfall, polar environments have slow nutrient cycles, meaning the soil is usually deprived of nutrients. The climate causes little wildlife to thrive, especially decomposers. Winter temperatures average minus 40 degrees centigrade in some polar regions, and precipitation almost never exceeds 100 millimetres a year. Characteristics: vegetation and soils. The cold, harsh climate with little rainfall also means only highly adapted vegetation can grow, such as mosses and lichen. These plants rarely decompose as there are a lack of decomposers. When plants eventually decompose, the cold temperatures cause this process to be extremely slow. This lack of nutrient-rich vegetation from the harsh climate causes the soil to be low in nutrients. The nutrient-deprived, frozen soil limits further nutrient-rich plant growth, and this creates a cycle where poor vegetation causes poor soil, and poor soil causes poor vegetation. Alpine environments. Current distribution. Alpine environments are areas of low temperatures in high altitudes, mountainous regions. These environments are found above the tree line. Characteristics: climate. Temperature in alpine areas fluctuate annually. The alpine summers are frequently above 0 degrees. An example of an alpine area is Mount Washington, the White Mountains. As seen in this graph, there is a large amount of fluctuation between seasonal temperatures. Characteristics: vegetation and soils. In the winter, alpine environments receive more heavy snowfall, more than in polar environments in most cases. In summer, milder temperatures can lead to heavier rainfall and a lot of meltwater from the melting of snow and ice. The climate allows adapted animals to move to higher altitudes. The milder temperatures also stimulate plant growth, thawing and decomposition. Vegetation that is adapted to the alpine environment thrives in milder alpine summers and usually dies back in winter. The climate and consequent wildlife allows for a quicker nutrient cycle, as the wildlife uses vegetation for food and the warmer climate encourages decomposing. Alpine vegetation is decomposed more quickly than the polar climates and grows quicker too, due to soil fertility and climate. Higher temperatures allow soils, usually at lower altitudes, to thaw, increasing the area that the vegetation can grow in. The nutrient-rich vegetation allows more fertile soil to develop when it decomposes, and the nutrients are transferred into the soil. This fertile soil allows more nutrient-rich plants to grow. Soils usually freeze in winter, meaning that less plants can grow in the colder conditions. Periglacial landscapes. Current distribution. Periglacial areas are found on the edge of colder environments like polar and alpine environments. These are consistently cold enough that the ground is permanently frozen in permafrost. Permafrost can be continuous, discontinuous, sporadic or isolated, which indicates the extent of the permafrost cover. Although permafrost is found on the fringes of glacial and alpine environments, the majority of permafrost is located at high latitudes within the northern hemisphere. Characteristics: climate, vegetation and soils. Similar to polar environments, precipitation is low, but still occurs during the summer months. Temperatures are consistently below freezing. The latitude of some permafrost regions also assists the consistently cold temperatures, as winters in higher latitudes last longer, with less daylight hours making them colder. Vegetation is more prevalent than in polar regions, but only highly adapted plants can survive in the cold temperatures with little rainfall. The temperatures and poor soil lead to a slow nutrient cycle. The lack of nutrient-rich plants contributes to soil infertility. The permafrost makes it hard for plants to grow, as plants cannot infiltrate the soil. The cold climate causes the lower ground to be frozen all year round. However, slightly warmer summer temperatures cause the thawing of the upper soil, called the active layer. Soil is usually extremely waterlogged in summer due to thawing, which means plants can become deoxygenated within the soil and cannot survive, and any nutrients are often leached out. Periglacial processes. Nivation. This is common in periglacial environments due to the fluctuating temperatures. Nivation is a collective term for processes involving snow and ice that causes erosion. Nivation hollows are created by nivation processes, which is where snow gathers in a small depression, and eventually this erodes into a full hollow of snow. Nivation hollows are the beginning of corries. The active layer. This is the top layer of permafrost that thaws in the summer. Frost heave. Water underneath rock or ground freezes, expands, and thus forces the masses upwards. Solifluction. This is the mass movement of soil that becomes waterlogged when soil is trapped between the active layer and the frozen permafrost. Waterlogged soil flows easily when gravity acts upon it, usually due to the gradient. Glacial systems and processes. Accumulation. The addition of mass to the glacier. This mainly occurs at higher altitudes at the source of the glacier. And ablation. This is the loss of mass of the glacier. This includes meltwater, avalanches, sublimation, evaporation, and other processes. The glacial budget. The mass balance of a glacier, i.e. the differences between the accumulation and the ablation. A positive glacial budget shows accumulation exceeding ablation, so the glacier is advancing. A negative glacier budget is when ablation exceeds accumulation, so the glacier is retreating. Glacial budgets fluctuate yearly, with more ablation in the summer months and more accumulation in the winter months. System features. Glaciers are natural systems, meaning there are specific interactions within their development, sustaining the glaciers, allowing them to work. In the concept of a natural system, something enters the system which allows the processes to occur, eventually leading to something leaving the system. It is an open system. There are inputs from the outside of the system's set area. In a closed system, all of the inputs and processes occur within the system's set area. The aspects of a system apply to the natural system of a glacier. The inputs. Addition to a glacier, these are the accumulations. Precipitation, such as snow or hail, are inputs to a glacier, as well as avalanches from other areas entering the system. Debris that has been eroded can also fall onto the glacier system, and consequently can be transported and deposited elsewhere. The outputs. Things that leave the glacier system, usually in the form of meltwater. All ablation processes are outputs. Carving is also a common output, in which large pieces of the glacier break off at the end. Energy. Glaciers all have varying amounts of energy depending on their mass, their environment, their composition, and other factors. For example, a glacier with more meltwater underneath would move it faster, giving it more energy. Glacial energy is usually in the form of kinetic energy as the glacier moves. This energy allows erosion to occur. Gravity allows the glacier to have energy as it forces the glacier downhill. Stores. These are also known as components. Stores are the mass that glaciers hold, but the majority of stores within the glacier are ice, but sediment from erosion and meltwater lakes and channels also contribute to the stores. There are 3 types of glacial stores: subglacial, beneath the glacier, englacial, within the glacier, and supraglacial, on top of the glacier. Flows. Flows occur in glaciers through the transfer of mass or energy. There are flows in mass and energy from the ice on the glacier to meltwater leaving the glacier. The glacier also moves through flows such as compressional flow. Dynamic equilibrium. Equilibrium refers to a state of balance. This balance is dynamic, where the processes causing the balance are continual, constantly occurring. For example, even if the glacier is constantly gaining inputs and losing outputs, if the amounts of these are not the same, the mass of the glacier does not change The mass of the glacier does not change annually, and the glacier is at a dynamic equilibrium. The area where mass gain is equal to mass loss on a glacier is called the equilibrium line. Feedback loops. A feedback loop is a type of chain reaction, where one process leads to another process, leading to another process, and so on. There are two types of feedback loops, positive and negative. In positive feedback, a process occurs, which causes another process to occur, which starts a chain reaction that heightens the first process. In negative feedback, the process that occurs is counteracted by opposing forces, causing the effect to cancel each other out and nothing to change. Ice movement. Glaciers always move under their own weight, which, with gravity, forces the ice to flow. There are different ways in which glaciers move. Internal deformation. The deformation of ice layers or individual ice crystals, caused by the pressure of the weight of the ice. This causes some layers to move faster than others, so different parts of the glacier can be advanced further. Compressional flow. When ice hits a shallower gradient, friction causes the ice to slow down, build up and compress. This causes the ice to get thicker. Extensional flow. When ice meets a steep downhill gradient, usually going over a hill, gravity forces the ice to increase in velocity. Friction causes the ice to thin out and extend, causing deep cracks called crevasses. Rotational slip. Compressed ice becomes trapped in a hollow, but gravity causes it to continue to move downwards. Meltwater assists in moving the glacier in rotational movement, causing it to continually erode the hollow. Basal sliding. Glacier sliding over the bedrock. This is due to the meltwater providing lubrication to the base of the glacier. The velocity and power of these movements is heightened by the composition of the glacier and the surrounding landscape. More powerful movements cause more erosion, creating characteristic glaciated landscapes. Temperature of glacial environments. Warmer temperatures would lead to more meltwater, causing more basal sliding to occur. Erosional processes would thus be heightened, so cold glaciers move more slowly. Mass of a glacier. Heavier glaciers move more under the force of gravity, and more pressure is created due to the weight. In itself, this pressure causes erosional processes, but it also encourages meltwater, which assists in erosion. Relief. The steeper relief heightens the effect of gravity on a glacier. A warm-based glacier would have a higher velocity, as meltwater assists lubrication. A cold-based glacier would struggle to move, building pressure and again causing more erosional processes. This could be classed as a negative feedback loop. The size of obstacles that a glacier must travel around affects the motion of a glacier. Creep occurs when a glacier travels around a large obstacle larger than a metre by plastically deformation. Alternatively, if the obstacle is smaller than 1 metre, the glacier will melt under increased pressure, and so the glacier accelerates due to basal slip. The glacier will refreeze on the lee side of the obstacle, which is known as regulation. Glacial environments. A glacial environment is an area where temperatures are consistently cold enough to sustain glaciers or ice sheets. Glacial environments are both in polar and alpine areas, and sometimes in periglacial areas. However, temperatures are often not cold enough. The climate, soil and vegetation is depending on that region in which the glacier develops. But the temperatures must be below freezing for long enough of the year that the glacier does not melt entirely. Development of glaciated landscapes. Glaciated landscapes are shaped by processes that create landforms. The three main types of processes that create these landforms are geomorphological, periglacial and fluvio-glacial. These processes are glaciated, periglacial and fluvio-glacial landscapes. Erosion. Plucking. Rocks attached to the bedrock or slides become frozen to the glacier. When the glacier moves, the rocks are plucked from the landscape, leaving a jagged surface. Abrasion. A sandpapering effect caused by small rocks embedded within the glacier rubbing on the bedrock. This usually leaves a smooth surface with scratches called striations. Crushing. For a weak bedrock, the weight of the glacier causes fracturing in the bedrock. Glacial crushing tends to produce large angular blocks of rock. Basal ice melting. The weight of the temperate glacier will cause basal ice melting. The large volume of water produced causes fluvial erosion. Hydraulic action, attrition, corrosion, which will all erode the base of the glacier over time. The development of landforms. Different landforms are created in certain cold environments. This table shows how landforms arise from different environments. Geomorphological landforms and glaciated landscapes. Corries. This is a picture of red tarn in the Lake District. Corries form where snow continues to build up in a depression or nivation hollow, eventually compacting to form a glacier. The glacier becomes trapped within the hollow, meaning the only way it can move is through rotational slip. The back wall is eroded through plucking and frost shattering, and the hollow is deepened through rotational abrasion. Water can fill corries to make tarns, lakes. As corries are eroded rocks, they last a long time and are minimally affected by erosion. This is why corries have lasted for thousands of years. Arêtes. This is striding edge in the Lake District. A knife-edged ridge formed between two corries when two steep back walls meet. If three meet, they call a point called a pyramidal point, pyramidal peak. Similar to corries, arêtes last a long time. Glacial troughs. A U-shaped valley caused by a glacier bulldozing and eroding through a river valley, a V-shaped valley. The glacier has enough force to erode its way through a river's interlocking spurs. This leaves a smooth but steep-sided truncated spurs on the valley sides and a wide, flat valley floor. The river that originally flowed through the valley will continue to flow, giving it the name a misfit stream due to its small size in comparison to the surroundings. U-shaped valleys last for a long amount of time. Hanging valleys. This is a picture of Fiordland National Park in New Zealand. The smaller U-shaped valley caused by a tributary glacier. The smaller glacier does not have enough energy to erode the valley floor, often leaving a hanging valley. Waterfalls can often form here. Hanging valleys last for a long time as they are erosional features. However, waterfalls can erode away a hanging valley over time. Roches matonnées. A mound of rock shaped by a glacier flowing over it and eroding it. The glacier will be moving right to left in this picture. The glacier hits an obstacle and is too large for it to pluck, so it must move over it. The glacier hitting the obstacle increases friction and pressure, therefore increasing melting as the lower ice can reach the pressure melting point. This meltwater allows the glacier to slide over the rock, and smaller rocks will abrade the stoss side. When glaciers reach the top of the obstacle, friction and pressure drop. Meltwater refreezes, and frozen rocks are plucked from the lee side. These landforms last a long time as they're made of rock. Depositional landforms. Till plains. Till is unsorted glacial material formed through erosion and weathering. Till plains form when ice sheets detaches from the main glacier and melts, causing all of the till on top of the glacier and within the glacier to deposit on the valley floor. Till plains can last a medium amount of time. They can be disrupted through meltwater, periglacial processes and weathering. However, due to their vast nature, till plains will usually still be noticeable. Erratics. This is a picture of Noba erratics in the Yorkshire Dales. These are large boulders of a different rock type to the surrounding rock. This boulder would have been broken off by weathering and erosion and then transported by the glacier and deposited when it had been moved to a different location. The glacier deposits when it loses energy. Depending on the size of the erratic, these can last a long time as they are too big to be displaced by weathering alone. Moraines. Deposits of eroded material that are transported within the glacier. There are different types of moraine. Lateral moraines. This is where deposited material on the sides of the glacier leave a ridge when the ice melts. Formed from two lateral moraines meeting in the middle of a glacier and depositing material. Grand moraines, carried under the glacier and abraded between the glacier and the valley floor. Grand moraine is the only sorted moraine as all of it is abraded underneath the glacier, whereas all other types of moraine are unsorted. Recessional moraines form at the end of a glacier when it is retreating. It usually stays stationary for a sufficient time. This usually shows smaller seasonal retreats. Terminal moraines. This is when material is deposited at the snout of the glacier on the valley floor. Moraines can be classified as lasting a medium amount of time. Although moraines are still present for thousands of years after glaciers have retreated, it can be displaced through meltwater during retreat or weathering. Drumlins. When a glacier hits an obstacle that cannot be eroded, deposition from underneath the glacier builds up over the obstacle. The glacier moves over the large mound and drags excess deposition over the other side. This causes a teardrop shape with a long tapered edge. The blunt end is the stoss side, whereas the tapered end is the lee side. Drumlins can be around 1,500 metres long and 100 metres high. Drumlins are usually found in groups called swarms. Drumlins can last a long time, but they can sometimes be disguised as depositional, meaning greenery can grow in the sediment. Fluvio-glacial landforms and fluvio-glacial landscapes. Meltwater channels. Streams of meltwater formed within higher temperatures. Channels can flow within, in front of and around a glacier. Due to the high pressure of a glacier, they are highly erosive. If meltwater channels lose energy, they are deposited and sorted material in small islands, creating braided channels. Meltwater channels will last a short amount of time because they only last for short periods of higher temperatures that will allow for liquid water. However, the eroded landscapes can last for a long time. Kames. Meltwater transports and deposits eroded material on a retreating glacier. Material collects within a depression on top of the glacier. When the glacier melts completely, the material is left on the valley floor. This leaves a mound of usually fine material. Kames are sorted, meaning the heaviest load will be deposited first and finer sediments on top. Kames will last a medium amount of time, as they can be eroded and weathered due to their composition. Eskers. A long winding ridge of glacial deposition. An esker is a mould of a glacial meltwater channel. Material is deposited when the subglacial meltwater channel loses energy. Due to the high hydrostatic pressure, the mound builds up and retains its shape. Eskers can last a medium to long amount of time. Due to their size, an esker is difficult to erode and weather. However, it is not as strong as erosional rock-composed features. Outwash plains. When a glacier recedes, a large amount of meltwater is released due to the higher temperatures melting the ice. The meltwater loses energy as it's under pressure, so it deposits the material in front of the glacier. Material is deposited into sorted layers. Gravel and rocks are deposited first and the finer sediment is deposited on top. The deposits can create alluvial fans, which is where the meltwater channels separate into smaller, fanned-out sections in order to take the fastest route through the deposited material. These plains last only a short amount of time, as they are only sediments, meaning they are easily eroded and weathered. In alpine regions especially, outwash plains are only seasonal. Periglacial landforms and periglacial landscapes. Patterned ground. Patterned ground is formed through frost heave of stones in and underneath the active layer. Ice lenses exist within permafrost, and they grow through repeated freezing and thawing. Capillary action draws more water to the ice lens, causing it to grow more. When the ice lens expands, stones around the ice lens are shunted upwards. Larger stones roll down due to their weight. Fine sediment fills the space to stop larger rocks. Polygons appear on flat surfaces or stripes on steeper inclines where the rocks roll downhill. This landform can last a medium amount of time, as they can be disrupted when periglacial landscapes become warmer, disrupting the ice lenses. Ice wedges. Water infiltrates small cracks in the permafrost and it expands on freezing. The water then fills the expanded ground. The process repeats and leaves a large ice wedge. The ice wedge is likely to last a medium amount of time, as temperatures must consistently stay cool enough for ice wedges to grow. Pingos. Ground is forced upwards through frost heave of an ice lens, leaving a mound. The mound can be open or closed. Open pingo formation. Discontinuous permafrost areas. Water moves through unfrozen ground between areas of permafrost. Due to capillary action, the water groups together. The water freezes and creates an ice lens. The ice lens continues to grow and pushes the unfrozen ground upwards. Closed Pingo Formation in continuous permafrost areas. Under a lake, permafrost is insulated and melts. The lake will eventually dry up and freeze, leaving the unfrozen ground. An ice lens will develop through capillary action when temperatures drop and the water groups together. When temperatures drop, the permafrost advances and frost heaves the unfrozen ground upwards, creating a mound. Pingos last a medium amount of time, as cracks in the ground let in water which melt the ice lens, and warmer temperatures also melt the ice lens. Terraquettes. The formation of terraquettes is not fully known or agreed upon in geographical study. There are a few theories of how they arise. However, the most common theory involves the intervention of vegetation. Frost heave pushes particles of soil upwards, which would usually fall downhill through the process of creep. However, vegetation blocks the soil from falling, meaning it stays behind in steep shape. The shape of terraquettes can be described as terraces. Terraquettes last a short to medium amount of time, as thawing of the soil would disrupt the process of frost heave. However, the extent of the landform means the area is unlikely to be cleared completely in the short term through weathering. Solifluction lobes. When the active layer and solifluction occurs, tongue-shaped lobes of soil fall down slope. Solifluction lobes last a short to medium amount of time, as the soil cannot retain this stretched structure for long. When the temperature rises, the soil moisture content will decrease. Block fields. A rock-strewn landscape caused by extensive frost action of the landscape. Block fields will last a medium to long amount of time, as loose rocks can be displaced through the weathering. Thermokarst. Marshy, boggy wetlands caused when permafrost melts. Any ice lenses within the ground originally, or landforms such as pingos, would melt and collapse. This can leave holes in the ground which will also fill with meltwater. Thermokarst landscapes last a short to medium amount of time, as they'll dry up when temperatures rise and permafrost retreats. Value of glaciated landscapes. Both relict and active glacial landscapes have value. They are economic, environmental, or of cultural significance. Polar scientific research, especially in the Arctic and Antarctic, is significant. Since these environments have had minimal human influence, they provide perfect measures of Earth's past environments. Rare wildlife is also monitored and researched. There are some spiritual associations with glacial landscapes. Indigenous communities such as Alaska's Tlingit people and America's First Nations base much of their culture on the snake-like being of glaciers. However, this environment is under threat. Environmental fragility. The concept of an environment being vulnerable and at risk, as it lacks the ability to be resilient and adapt to changes. Fragile cold environments. Cold environments are classed as environmentally fragile due to a number of reasons, causing small changes to have a large and destructive impact. Highly adapted ecosystems. Plants and animals must be highly adapted to the extreme weather conditions around them in order to survive. Especially in polar regions, plants and animals have adaptations to allow them to survive in cold temperatures. Therefore, when something changes, such as the temperature becomes higher, these highly adapted species find it more difficult to cope with the changes. Slow nutrient cycle. Due to the cold temperatures and nutrient-deprived environment, cold environment nutrient cycles are slow. This means that things will take longer to break down and longer to restore when they are damaged. Plants cannot regenerate as quickly as in other environments, which limit their growth indefinitely. This means that if litter or other foreign objects are placed in the environment, they will take a long time to decompose, which can affect plant and animal behaviour. Lack of biodiversity. Due to the cold, unforgiving climate, only certain plants and animals survive, meaning food chains are limited and species depend on each other. If a species is removed or damaged, this can spread through the entire food chain, affecting every aspect of the ecosystem. For example, species of krill is declining in the Antarctic, which is causing penguins to migrate to different areas, affecting seal populations. Human impacts. A major threat to cold environments is the effects that humans have on them. Humans affect cold environments through direct intervention or through passive contribution. Humans can affect cold environments directly at a local scale, such as dropping litter in an alpine environment. However, they can also contribute at a regional and global scale through pollution and oil usage. Tourism. Tourism is a recent but present problem in cold environments. Alpine tourism is the most prevalent and oldest form of cold environment tourism due to mountainous regions being used for ski slopes. The displacement of ski resorts increases urbanisation and construction, displacing wildlife and the ecosystem. Humans in alpine areas disrupt the ecosystem by destroying plants in snow sports and scaring wildlife away. Any litter dropped will stay in the nutrient cycle for a long time, as decomposition is slow. Tourism in other cold environments is also a growing industry, especially in Antarctica due to the rise in extreme tourism. Antarctica is arguably even more fragile than alpine environments, meaning any foreign object entering the ecosystem is likely to have a catastrophic effect on the pristine and untouched environment. Sea ice distribution and cruise ship crashes are also contributors to environmental destruction as tourist numbers increase. Resource exploitation. Polar and periglacial environments especially have become an abundance of natural resources, such as minerals and oil. These regions have therefore become at risk to over-exploitation and habitat deconstruction. Oil exploitation disrupts the habitat through the infrastructure that comes with it. Oil spills can also be catastrophic damage to periglacial and polar regions, as the fragile ecosystem cannot move oil quickly, affecting the ecosystem. Material and mineral exploitation damages the environment through mining and quarrying, scarring away wildlife and causing damage beyond repair. Currently, Antarctica is protected from this exploitation, but it will not stay in the future. Fishing and whaling. Polar regions are especially under threat from unsustainable fishing in these areas, which disrupts the food chain. These are fragile environments. Sealing and whaling began as far back as the 18th century, and although there are currently bans on almost all whaling, whale populations still stay at reduced and endangered levels from the damage previously done in the past. Other fishing has increased in the 20th and 21st century, and there are still reports of illegal, unreported and unregulated fishing. This fishing is unsustainable and causes wide-scale marine habitat damage. Overfishing removes vital animals in the food chain, such as overfishing of krill, which removes other marine animals' food sources. Pollution. Pollution is a large-scale problem affecting cold environments. There is local pollution issues associated with leaving litter. However, pollution is also a global issue due to the combustion of fossil fuels. Global warming. Furthermore, global warming is also threatening these glaciated landscapes. The combustion of fossil fuels causes a variety of impacts for cold environments, often setting up a positive feedback loop, in which an impact can quickly spiral or create a worse impact. Global warming is a major issue for cold environments. Warmer temperatures cause melting, which is clearly bad for cold environments. Permafrost melts, glaciers retreat, and alpine environments thaw for longer summers. This melting causes further issues. Local floods near glaciers, regional floods if rivers carry water elsewhere, global floods if major ice sheets and glaciers melt, causing sea level rise, disruption to flora and fauna that are adapted to the environment. CO2 is released into the atmosphere that is stored in the ice sheet and permafrost. The albedo effect is lessened due to less ice sheets. This is the idea that white surfaces, ice, reflect solar radiation back into the atmosphere, meaning that more heat is absorbed into the oceans. Higher regional temperatures affect cold environments in other ways. Invasive species are adapted to higher temperatures and have grown and caused the colonisation of some cold environments. Migration patterns of certain animals have been disrupted by the higher temperatures. For example, the strandings of polar bears migrating to lower latitudes in winter. Food chains are disrupted by migration changes and invasive species. Management. As cold environments are so fragile and in need of protecting, there are current strategies that should be put in place to conserve these regions. It must also be considered how cold environments should be managed in the future, especially due to future worries into climate change. Current management of cold environments. Tourism. Sustainable tourism is becoming a growing industry, helping to reduce the effects that humans have on their trips to fragile cold environments. Charities such as WWF are promoting sustainable alpine tourism in order to protect these areas. Polar extreme tourism. In most cases, a positive management of these cold environments. Encourages a positive management of these cold environments. Visitors are limited, so only smaller cruise ships can attend the land. Cruise ships must also have a permit, and regulations are very tight. For example, shoes must be checked for foreign objects so that they do not enter the ecosystem. Tourists are also encouraged to become aware of the risk of cold environments and contribute to charities. Cold environments are also protected by law in some areas, such as areas of permafrost in Alaska that restrict access and construction. Exploitation. Many cold environments are protected by law so that any natural resources cannot be overexploited. For example, the Antarctic Treaty and Madrid Protocol have banned mining in Antarctica. There are also extensive fishing quotas and monitoring systems in polar environments as to protect the ecosystem, as well as a ban on all military activity. Climate change. There is little to be done that can stop the effects of climate change on cold environments. Globally though, there are strategies in place to mitigate climate change so that it may not have such catastrophic impacts. International agreements and conventions are attempting global cooperation. And that is the end of this episode. I really hope you didn't mind. The builder, he's really annoying me. He just keeps doing stuff. You can probably hear him. And the cockerel, I can't shut that up, but they've been really annoying. So I hope you enjoyed. Do subscribe down below. I am going to be doing more of these when they've shut up. But yeah, subscribe down below so you don't miss out on the next one. Bye guys.